Today we start one definition from one definition. Okay, this definition also gives some algebraic element, okay, and transcendental element. That means let if extension of k, okay, if extension of k, then be a field extension, be a field extension, an element A belongs to this F, okay, is said to be be algebraic over K, okay, if there exists K0 K1 Kn belongs to K, not all zero, okay, such that K0 K1a Kn a to the power n equal to 0, okay, there exists this one such that this holds, okay. So an element this one be algebraic if this satisfies, and otherwise this A is called transcendental over K, okay, transcendental over K. That means one element when algebraic and when transcendental, this depends on this one be a root of some polynomial or not, okay. This one be a root of polynomial, then this element is called that means algebraic over this field K, okay, and otherwise this one is transcendental, okay. Now we also give some example with respect to this definition, okay. We start here. Example: the element root 2, okay, in R is algebraic over Q since root 2 is a root of x square difference 2 belongs to this Qx, okay. Next example, it is our portion and going to further discussion of that. The element I belongs to C is algebraic over R, and Q. That means over R and Q also. Since I is a root of, since I is a root of x square plus 1 equal to 0. Okay. That means root of this equation also root of this, sorry, that means this one. Okay, this one belongs to, this polynomial belongs to qx, and also this one belongs to rx. Okay, now we also known about that pi and e. Okay, pi and e, this one belongs to R, obviously transcendental over q. Okay, pi and e, this one be transcendental over q. This one be not a root of any polynomial. Okay, or any equation not gives this root. Obviously this equation's coefficient are belong to R. This one is not possible. So this two number pi and e we call transcendental. Okay, now we going to discussion one theorem. Okay, we erase that portion and going to discussion one theorem. We write the statement of this theorem first. Let if extension K be a field extension and C belongs to F, then C is algebraic, then C is algebraic over K if and only if C is a root of some unique irreducible monic polynomial px over K. Okay, so we also start proof of this theorem. That means if extension of K be a field extension, C belongs to F, C algebraic over K if and only if C is a root of some unique irreducible monic polynomial Px over K. Okay, then we write this proof now. Suppose C is algebraic over K. There exists a non-zero polynomial fx belongs to kx such that c is a root of fx and fx does not belongs to k. Okay, C is algebraic over K. There exists a non-zero polynomial fx belongs to kx such that C is a root of fx and fx does not belongs to k. Okay, then by previous theorem, okay, there exists irreducible polynomial okay, f1 f2 dot fmx, okay, belongs to kx such that fx equal to f1x f2x dot fmx, okay, thus what, thus 0 equal to fc equal to f1c f2c dot fmc. Since f has no zero divisor, since f has no zero divisor, we must have fic equal to 0. We must have fic equal to 0, okay, and any one 0, otherwise if zero divisor exists, then this two non-zero multiplied gives 0, okay, but this one is not possible, so here fic equal to 0. Okay, here also given this one is filled, okay, so this one not possible and this one anyone is 0 for some I, okay. So what happened after that? Thus there exists an irreducible polynomial. Thus there exists an irreducible polynomial Okay, there exists an irreducible polynomial hx, okay, hx equal to b0 b1 x dot b2 x square plus bm x to the power m, bm not equal to 0, okay, such that what, such that hc equal to 0. Okay, then now let px equal to what, px equal to bm inverse hx. Then px is an irreducible monic polynomial in kx. Okay, then px is an irreducible monic polynomial okay, in kx with c as a root. Px irreducible monic polynomial with c as a root. Okay, now we erase our portion also. Let gx be a polynomial. Let gx be any polynomial. Okay, in kx. Okay, in kx which has c as a root. Okay, which has c as a root. Let px be a monic polynomial. Be a monic polynomial. Okay, of smallest degree. Of smallest degree in kx. Okay, which has c as a root. Okay, which has c as a root. There exists qx rx belongs to kx. Then what happened? Then there exists qx and rx belongs to kx. such that what gx equal to qx px plus rx. Okay, such that gx equal to qx px plus rx, where either rx equal to 0, where either rx equal to 0 or degree of rx less than degree of qx. Okay, then what happened? Then now this one 0 equal to gc equal to here qc pc plus rc. Okay, that means qc multiplied 0 plus rc. Okay, then what happened here? Thus rc equal to 0, thus rc equal to 0 when rx equal to 0. Okay, else we contradict the minimality of degree px. Okay, we contradict the minimality of degree px. Okay, of degree of px. Then here that means thus px divides gx in kx. Okay, thus px divides gx in kx. Okay, otherwise in this way. Now let Sx be any irreducible polynomial in Kx. Let Sx be any irreducible polynomial in Kx. Okay, in Kx, then what happened? Which has C as a root. Okay, which has C as a root. Then Px divide Sx also. Then Px divide Sx. So it is lower portion also. Then what happened here? Then चुप करो. Then Px is not a constant polynomial. Then Px is not a constant polynomial in Kx. Okay. Since it has C as a root. Since it has C as a root. Okay. Then now Px is not a constant polynomial. Obviously Px not constant polynomial in Kx since C as a root. So thus since Sx is irreducible, since Sx is irreducible in Kx, okay, and Px must be irreducible in, then Px must be irreducible in Kx. Okay. Then what happened? That means also Px equal to Ksx for some k belongs to K. Now if we choose Sx is monic, if we choose Sx monic, okay, then K equal to 1. Then K equal to 1, okay, and so we have the desired uniqueness property of Px, okay. So Px unique. Then this one, that means we also, and now converse part, okay, converse part, that means we also prove that this one be a C is a, that means C is a root of some unique irreducible monic polynomial Px. Then obviously that means C is a root of some polynomial, that means C is algebraic, okay. This one is not, that means by definition this one hold, so easily this one is done. So we complete this proof now. So this today I stop here. If you get this type of video, please subscribe and follow this channel, okay. And obviously if you that means please click on like option and give some like if you that means want to satisfy this problem, okay. So today I stop here.